Hey everyone, how's it going? Today we're going to be talking about the building blocks of God's reality, the physics of God's creation. And it's pretty amazing that physics and the Bible actually do go hand in hand, and you don't have to sacrifice one for the other. Now, for those of you who might be watching that, excuse me, hang on one second. It's pretty amazing that physics and the Bible actually do go hand in hand, and you don't have to sacrifice one for the other. Now, for those of you who might be watching that, excuse me. Hang on one second. It's pretty amazing that physics and the Bible actually do go hand in hand, and you don't have to sacrifice one for the other. Now, for those of you who might be watching that, excuse me. Hang on one second. It's pretty amazing that physics and the Bible actually do go hand in hand, and you don't have to sacrifice. Okay, sorry about that. I guess I had my YouTube window open, and it was playing through my speakers what I'm saying, and I was getting a feedback loop. Anyway, okay, sorry about that. So moving on. As I was saying, you don't have to sacrifice science for the Bible, nor do you have to sacrifice the Bible for science. So for those of you out there who are just strictly science-minded and don't have any real interest in religion or Christianity or the Bible, that's okay. You'll still get a lot out of this video, and maybe it'll help you think of things in a different way. At least consider the possibility. And for those Christians that are watching that really want nothing to do with science and just want to focus on the Bible, that's okay. But I'm hoping that it'll do the same. Maybe let you see things in a different way, or at least consider some new possibilities. So Psalm 139:14, we can start there. It says, I will praise thee, for I am fearfully and wonderfully made. Marvelous are thy works, and that my soul knoweth right well. So it's actually part of spirituality to kind of marvel at the creation, to look at what God has done, or to look at physical reality and appreciate it for what it is. So that's what we're going to look at today. And also, for those who might see the title and think, quantum physics, that's a scary word. This isn't going to be over your head. This is something anybody can understand, because I really do believe that even a field like quantum physics should be for everybody. The problem is a lot of physicists, they work around other physicists most of the time, so they speak their own language. Really, it's just getting over the language barrier more than it is having to learn a bunch of complex things. So the big picture ideas, I believe anybody can understand. And, I've said this in other videos before, but I wrote a book, Quantum Creation. That's where some of this information is going to come from. But I've had teenagers write me and say that they love it and understand it just fine. And I've had people in their 70s or 80s write me and say the same thing. So this isn't going to be over anybody's head. I'm sure a lot of this will be new, but hopefully it'll help spur on some more study. So we can talk about particle physics. Now, the studies of particle physics and quantum mechanics, those terms, seem kind of big and scary, but they're not. Really, physics is just how something behaves naturally, just what its natural state is. So if we're talking about particle physics, then we're just looking at how particles are naturally. Now, quantum mechanics, the word quantum just means the smallest of the small. So the smallest building block of reality is called like a quantum particle. It doesn't break down into anything more than what it is, like a photon, which is a particle of light. We would call that a quantum particle because a photon isn't made of other particles that we know of, at least that we know of yet. It might be, with further research and study, we might find that it is. But so that's what quantum means. The plural of quantum is quanta. And then mechanics, it's again just how it behaves naturally, how it moves specifically. So these fields are really fascinating, and they're the studies of the literal building blocks of matter and energy. They're a direct look into the materials that God used in his creation. So they define a world so strangely different than our own, even though our world is made up of that world. But it's so strangely different, which is strange. It's a world full of unpredictable behaviors and head spinning contradictions. If there's anything in the world that has the potential to instill an automatic humility in a person, it's a study of the building blocks of the world itself, or of reality itself. Just when humanity thinks that we have a fair grasp on reality, something else is discovered that throws everything else for a loop. So Proverbs 25:2 says, "It is the glory of God to conceal a thing, but the honor of kings to search out a matter." And that's especially true in the area of study. Okay, before we continue, if you haven't done so already, please subscribe to my channel. There's a little subscribe button in the corner of your screen. Just hit subscribe. Make sure you subscribe to my channel, and you'll get videos like this. We also have the Sharpening Report on here, hosted by excellent hosts James DeWitt and Jake Rahutsky. It's an interview show. You'll love it. And we post all sorts of cool and different things on here. So just make sure you subscribe. Make sure to share this video. Okay, so I've done a few of these videos. If you haven't seen the other ones, that's fine. You don't have to know them to know this. They can stand independently. But the research in this video, I almost hesitate to use the word series, because it's not really a series. It's just a collection of individual videos that they're different. But when I say series, it kind of makes it sound like you have to watch the others to understand this one, and that's not true. So any reference that we have to the other videos, I'll make sure to explain it. So if you do want to watch the other videos, that's great, but you don't have to understand this. So until now, in the other videos, we've pretty much looked at things that are more theoretical in nature. So no one has been able to scientifically observe a higher dimension or anything like that. And we will get back into theoretical issues in future videos. But for this one, or at least part of this one, I think it'll serve our purposes to define some of the things that have been scientifically observed and measured. And it's the attributes and behaviors of these building blocks that lead to theories concerning things of an even smaller size, right down to the Planck length size. As we talked about in the video previous to this one, Planck length is the shortest amount of distance that can be measured possible. Can't cut it in half, because then you get the obstacle of a black hole. So if you're interested in that, you can check out the video 10 Dimensions of Heaven and Hell. And there's more on that. But basically, just for this video, the Planck length size is the absolute smallest, shortest distance possible. So when we talk about Planck boundaries, that's what we're talking about. Planck time is the shortest duration of time that's possible. And the exciting thing about that is it shows that there are limits to our reality. There are actual boundaries put in place. So that's kind of cool to think about. Now, some of the things that are going to be discussed here might bring you back to the days of high school science class. I'm going to try to not make it as boring as that, because if you're like me, I did terrible in high school science. Now, some of these things might not have anything to do with that, but don't be mistaken that this will not be your average lesson in the basic of particle physics or anything. These are things that I'll present that you might actually find totally shocking. Now, for the benefit of the viewer, I'll cover only the essentials of understanding the rest of what we'll be talking about in this video. And like I said before, hopefully provoke further study on your own in any given area. Usually when these types of explanations are done, they begin with larger particles and they work down to the smallest. But since larger particles are actually made up of the smaller ones, I think the best way is to start at the smallest of the small and work our way up from there. So we're going to be talking about some terms, but don't worry, we're not going to spend forever on this part of it, but it's kind of important to know, and it is interesting. Again, we're talking about the building blocks of God's creation, what he actually used to construct reality. So we can start with fermions and bosons. These are the most fundamental and basic building blocks known. So as I stated earlier, some might point out that a molecule or an atom would be a better place to start. But I find that explaining what a molecule is while possessing the knowledge of the atom and the atom's constructs is easier than explaining what a molecule is without knowing about an atom or what an atom is made of. So it's easiest to start with the smallest. So fermions and bosons are what are known as elementary particles, or what we talked about before, fundamental or quantum particles. These are the smallest particles that we know in existence. Anything smaller than these elementary particles is theoretical. Fermions are generally matter particles that make up matter. Bosons are force particles, or a particle that carries a force, such as the Higgs boson. Matter particles would include things like quarks and leptons, and it's okay if you don't know what those are. Force particles would include gauge bosons, the Higgs boson. Now, even antimatter particles, such as antiquarks and antileptons, would be considered fermions. They're still matter particles, and the only thing that makes an antiparticle is it just has a different charge. So we'll be looking at that. Okay, so basically I did a lot of explanation of stuff that you probably don't need to know. Fermions are matter particles, bosons are force particles. That's about all you need to know. So the job of bosons is to determine interactions among fermions. So how matter particles interact with one another. That's a job of a boson, or a force particle. So probably the most well-known fermion is a quark. Quarks are of the smallest particles known. However, one would not find a quark just on its own. Quarks combine to create what are called hadrons. Now that word might sound familiar because we have the Large Hadron Collider at CERN. So quarks combine together to create hadrons, and hadrons themselves can either be what's called composite fermions or composite bosons. But basically, if a hadron is a composite fermion, it's known as a baryon. I know this is getting confusing. Don't worry, we're going to power through this and get onto some cool stuff. But if a hadron is a composite boson, it's known as a meson. Okay, it's okay if you forgot all of that. There are 6 different types of quarks, and these different types are called flavors for some reason. So the 6 different types are up, down, strange, charm, bottom, and top. Up and down quarks are known as first generation quarks. Strange and charm are second generation, and bottom and top are third generation. So for every quark flavor, there's also a corresponding anti-quark. So up and down quarks have the lowest mass, they're the lightest, and are the most stable, which means they don't easily degrade into something else than all the other quarks. Strange and charm, bottom and top quarks, they're less stable, and they can only be produced through high energy collisions, such as cosmic rays and particle accelerators. So CERN, the LHC at CERN, would be an example of this. Now I'm going to switch to screen share here because I got a chart that might help explain some of this a little bit better and why it's important. So here's a chart that shows the generations of quarks. So first generation here, second and third, and then here's the charge, plus 2/3, minus 1/3. Over here, you have the less mass particles. Over here, more mass particles. Okay, so moving on, talking about charge. Quarks have different types of electrical charge. Depending on the quark, the charge is either plus 2/3 or minus 1/3 of the elementary charge. And remember that word elementary. An elementary charge is the electric charge carried by one proton, a single proton, or the opposite of the electric charge carried by an electron. Stay with me. I promise this is going somewhere. To just get through this quickly, the up charm top quarks, which are referred to as up-type quarks, they have a charge of positive 2/3, while down, strange, and bottom quarks, known as down-type quarks, have a negative 1/3. So we see that here. All right, we're going to get into something interesting. Now, antiquarks, on the other hand, they have an opposite charge of their corresponding quarks. Okay, so a lot of that, this is just stuff on charge that it's not super important. Now, there is a lot more that we could get into concerning quarks. They do have a lot more attributes and strangeness than what we could cover, within one book or within one video like this. So, but that's enough about quarks. Now, nucleons. This is actually interesting because it shows how artistic representations like this are not accurate as to how strange reality really is. Okay, so in simple language, nucleons are what the nucleus, or the center, the middle part of an atom are made of. So you have an atom. The nucleus is what's in the very center. There are two known types of nucleons. Now, nucleons are particles that make up the center of an atom. So you have neutrons and protons, and both of those fall into the category of nucleons. So these nucleons, they bind together to form the atomic nucleus, the nucleus of an atom, the center of an atom. So most examples and models of nucleons, they kind of show them as these different colored balls like this, like figure 23 here. This is an example of an atomic nucleus with differently colored balls representing protons and neutrons. So you could say the red ones are protons, the blue ones are neutrons. A lot of models show that, but that type of model isn't exactly accurate. Now in reality, and this is really strange, each of these particles, each of these nucleons, they would be in multiple places at once, spread throughout the nucleus. Now, there's no real great way to model something that bizarre, but they would be in multiple places at once. They'd be popping in and out of existence. It's just a really weird thing that makes up the center of an atom. But just for sake of ease, they usually do it this way. So protons are made up of 3 quarks. You have 2 up quarks and 1 down quark, whereas neutrons are made up of 2 down quarks and 1 up quark. So we can look at figure 24 here, a proton and neutron with corresponding quarks. So simple enough, you have the 2 up quarks here, down quark, and then, all right, so this is a proton, this is a neutron. And again, I know a lot of this stuff is like, who cares? But and that's okay. That's okay. We are going to get into some cool stuff like string theory and branes and multiple dimensions and stuff like that. But this is a good foundation, and I promise I'm not going to spend any longer than I have to on this. Okay, so protons have a positive electric charge, which is why they're called protons. Neutrons have no electric charge, so they're neutral, so neutron. The mass of a neutron is a little bit more than a proton, and the nucleus of every atom consists of at least 1 neutron and 1 or more protons. The only exception to that is hydrogen, -1, sometimes known as protium, which consists of only 1 single proton. Okay. And we talked about an elementary charge. It's the electric charge carried by a single proton, or the opposite of electric charge carried by an electron. Now, again, we're talking about the building blocks of reality. God actually put all this stuff in place. He had to think about all this stuff and put it into place like this, which it's amazing to think about. So electrons. So now that we know what the nucleus of an atom is, the center of it, we can look at the other part of the atom, the electron. Now, electrons are really weird subatomic particles. And subatomic just means smaller than an atom. So they have a negative elementary charge, and their mass is only about 1/1836th of a proton. So if we were to put that into perspective, it's the same weight relation as a 2-month-old kitten to an average-sized car. So if you have a car, that's the atomic nucleus. The kitten would be the electron. So the electron was once recognized as an elementary particle because it had no known substructure, meaning it's not made of anything. And in essence, it was thought to be made of nothing at all. As early as 1980, it was thought the electron would be made of 3 different components, and these three components were theorized as being a spin-on, providing spin, an orbiton, providing the orbit, because electrons orbit around the atomic nucleus, and a holon, which carries the electric charge. In 1996, physicists seemed to split the electron into a holon and spinon. Then in 2012, Swiss and German researchers observed a split of the electron into a spinon and orbitron. There's a link there if you're interested in that. So that's interesting that it actually might be made of other things, even though we still generally refer to it as an elementary particle. Okay, 1913, and fascinated by the atomic structure, Danish physicist Niels Bohr, that might be a name that sounds familiar. He published the first quantum theory of the atomic structure. The theory wasn't perfect, but it did spur on the development of modern quantum theory. Bohr stated that electrons can only have certain orbits around the nucleus of an atom, and he showed that the lowest energy orbit would be closest to the nucleus. He also said that electrons could jump from one orbit to another. They would jump to a higher orbit when they received energy, and as they lose energy, they would jump back down, emitting light in the process. So that's what we're seeing here. This little squiggly line, that's the light, and this is the electron jumping orbits. So as it gains energy, it would go further out. As it loses energy, it would come further in. Okay. So I'm going to take it back off screen share here. Okay. Now, again, we're going to be talking about some other cool stuff. This is just kind of foundational, but the color of light depends on the difference in energy between the two orbits. It's the electron orbiting around the atomic nucleus which makes up the atom. That whole system is the atom. So different numbers of different variations within the constructs of the atom determine what type of atom it is. Now, interestingly enough, something called the double slit experiment. We talked about this in other videos. In 1961, Klaus Janssen discovered that a beam of electrons could behave as particles and as a wave, also known, and there's a fancy term called wave-particle duality. It talks about that. So the weird thing about that, though, is this experiment shows that you can only determine the probability of the path that an electron will take on its journey. You can only determine the probability. There's more chance that it'll go here rather than here. If an attempt to measure the electron directly is made, it actually destroys the experiment. It alters the results. And we talked about that in other videos. So that's the part of the weird and interesting world of quantum mechanics. Due to measurement and observation, a particle can actually be altered. Now, it's not, and that'll bring us to the strangest particle, the photon. But just to stay on this idea for a second, a lot of New Age practitioners have taken that idea and they've said things like you can create your own universe around you, and that's not exactly what the double slit experiment shows. It's not consciousness exactly that's doing it. Basically, if we think about what we are, we're a big collection of particles. You know, our bodies, our existence in physical space. We're essentially just a collection of different particles, all interacting with one another. So if you have one single electron that you're trying to observe, basically what you're doing is you're putting yourself, or it doesn't even have to be you. It could be a machine or a detector or anything. It could be a big pile of bricks. But when you put a big enough collection of particles close enough to the experiment, it alters the results because it's interacting. There's also the idea of, in order for us to see something, we need light. So when you're working on something on a subatomic level and you add light to the experiment, you're creating more interactions there. You're ruining the experiment, but we can't see it without the light. So it's for reasons like that. It's not that we consciously are creating our own reality around us and we're our own gods and all. It's none of that. It's just different interactions. Okay, so photons. This is actually really interesting. Photon particles. They come in a familiar form, that of light. So we encounter photons every day of our lives. Yet many times we're unaware of the miraculous beauty that surrounds such an astonishing creation. Now, while light is made up of particles called photons, experiments also show beyond question that light is a wave. Light is so strange, in fact, that it's been theorized that light is actually a vibration from the fourth spatial dimension. And if you're interested in that, you could check out a book called Hyperspace by Michio Kaku. But keep in mind, it was written years ago, and a lot of the information is out of date. This was when they were still believing there were 26 higher dimensions and stuff. But this theory about light, it's especially intriguing when we consider the account of creation in the book of Genesis. We read in Genesis 1, 3, and 4, and God said, "Let there be light," and there was light. And God saw the light, and it was good, and God divided the light from the darkness. So it's possible that this account is describing the moment that photons came into physical existence. Sometimes it's interpreted as saying that the light that came forth was the light of God. And in some ways, that's true, in the sense that everything in existence comes from God. Yet notice it says, "and there was light," implying that there was not light beforehand. So this is most likely describing the light of our physical universe that comes in the form of photons, not necessarily the holy and eternal light emanating from God, because that's eternal. So to further support that idea, notice it says, "and God saw the light," also implying that there was not light to see beforehand. So clearly, all throughout the Bible, God is described as being radiant. He's full of light. Yet this is not the same light being described here in Genesis. The light that is being described here is the physical light that was created by God. It's something new, something that wasn't before. So it's within time. So in essence, this is our normal, everyday physical light created from the holy light of God himself. So the idea that light is a vibration from a higher dimension might actually be accurate, and strangely enough, it might be able to be supported using the Bible. Now, there's another really interesting quality of photons. This not only exemplifies God's eternal nature and omnipotence, but in my humble opinion, it shows a bit of his sense of humor. Einstein's relativity, which is a topic that we'll get into in probably the next video when we talk about time. Einstein's relativity shows that as you increase your speed, time for you actually slows down as compared to somebody else who isn't moving. So it's not just that a clock would run slower. It's biological as well. Your metabolism, your brain synapses, breathing, heart rate, everything else actually slows down. So this effect of high speed is something that has actually been measured on a relatively small scale. Einstein also showed that one cannot travel faster than the speed of light. So as you travel faster and faster towards the speed of light, time literally goes slower and slower. Now, if you actually could travel the speed of light, which is, of course, technologically impossible in our present age, time would actually literally stop. Now, photons, which could be described as the carriers of light, photons exist at the speed of light. Now, this is really trippy stuff. This means that photons never accelerate to the speed of light. They just exist exactly at the speed of light. The consequence of this is, from the photon's perspective, time doesn't exist at all. This means that as soon as a photon is emitted from its source, even if it's a star millions of light years away, it immediately reaches its destination at that exact moment. There's no time in between for the photon. Now, this, of course, it's just from the photon's perspective. From our perspective, we could look at a star a million light years away and deduce that it took the photons from that star a million years to reach our eyes, or whatever. But from the perspective of that photon, it was absolutely instantaneous. So the fact that time doesn't exist from a photon's perspective can be compared to God himself existing outside the bonds of time and space. So since time does not exist from the perspective of photons, they never change. There's no time to change. It's impossible. It's the same with God. He doesn't change. So I think that's really interesting. Another interesting thing about photons is their ability to communicate with one another by means of something at an instant. And again, this is something that requires no time to actually work. Now, Einstein called this spooky action at a distance, and he wasn't a fan of it at all. But we would recognize it as quantum entanglement. And even though Einstein didn't really believe in it, it's proven to be true. There's lots of experiments that have shown that this actually happens somehow, and it's by means that are not understood. We don't know how this happens, but somehow photons can communicate with one another across vast distances at faster than light speeds. And actually, it's not even a faster than light speed. It's immediately, directly, at an absolute instant, they do this. Now, of course, that would seem to be impossible. So it's no wonder that Einstein wasn't a fan of this idea of quantum entanglement, but by various means, it has been shown to be true. Regardless of how far away they are from one another, photons can communicate with each other instantaneously, even if it's across the observable universe. So how that works is a complete mystery. And the thing that I find kind of humorous about photons is how drastically different they are in reality than what we would normally perceive. Light is something that's all around. It's all around us. We kind of take it for granted because we don't really think about how strange and weird it is. It's just always here. Now, the same could be said about God. We tend to see him in certain ways, but a lot of times God doesn't fit into our idea of reality. God doesn't seem to represent himself in many, or God does seem to represent himself in many ways throughout his creation. So much like his creation, the photon, God far surpasses all logic and reason. So he's ultimately eternal and timeless, again, like the photon. So I think that's kind of interesting. Okay, that's enough about particle physics and that kind of stuff. I want to talk about some more really cool things. Job 26:14 says, "Lo, these parts of his ways, these are parts of his ways, but how little a portion is heard of him, but the thunder of his power, who can understand?" So here we're going to talk about just from the smallest to the largest, just bounds and aspects of reality. So we can talk about strings and branes. And when we're talking about branes, we're not talking about like the brain in your head. It's short for membrane, B-R-A-N-E-S. And then strings, we're going to talk a little bit about string theory. So if you keep watching this video, string theory will make sense, I promise. So earlier we went through some subatomic particles, and that probably was the driest part of this video. But we did that in order to show the basic building blocks of what reality is as we know it. Now, of course, any study such as this, it begs the question, what are subatomic particles made of? If it's the smallest of the small, how can it just be made of nothing? Nothing is nothing, doesn't exist. So how can something be made from nothing, and of course it can't. But that's what we're talking about here. So it seems everything's got to be made of something. If not, how could anything exist? We may also wonder where this leads. Atoms make up the Earth, which is in the solar system, which is in the Milky Way galaxy, which is in our universe. But where does that end? Is there anything larger than our universe? So these are questions that we're going to address going forward in this video. The simplest answer is nobody knows. Easy enough, end of video. I'm kidding. But that is just the easiest and most honest answers, that nobody knows. But there are some very interesting ideas within the realm of physics that might provide answers. Now we're going to be delving into the strange terrain of string theory and membranes, but I'll remind you these ideas, they are theoretical at this point, so it's not like a proven fact. It's just speculation. It's fun to think about. And there are some very specific mathematics to give these ideas credence, but that shouldn't intimidate you. And I'm not really a math guy. When it comes to math, I know just enough to get by, but I don't like dealing with it. I like dealing with the big picture ideas. I like, and the reason for that, because sometimes people might wonder, well, if you don't do the math yourself, how can you trust it? Because 1 + 1 is still 2, whether you're an atheist or Christian. So the math, it's all on how we interpret the math. And that's what I like to do. So now, the terrains that we're going to be looking into, certainly strange. We're still talking about God's creation. So presented here, it's just an idea on how he might have gone about setting everything up. Now, it would not surprise me in the least if all of these things someday were proven as total nonsense. I mean, if you think about history, I mean, even 100 or a couple hundred years ago, 1,000 years ago, what they thought reality was and how it worked is completely different, and there have been a lot of different experiments to show that. So it wouldn't surprise me if the Lord tarries, if in another 100 or a couple hundred or 1,000 years, if we as humans learn a lot more about our universe, and the stuff that we're talking about today, it just seems ridiculous. I mean, we can almost expect that to happen because history has proven that time and time again that happens. So again, it wouldn't surprise me if everything that we're looking at in this video is proven as just total nonsense someday. Yet it also wouldn't surprise me if these things are someday proven true, because there are good reasons why people believe these things, and you know, there is real math around it. So all we can do for the time being is just speculate, you know, make educated hypotheses and have fun with it. Of course, the things discussed here, they go a bit beyond that, given that there are solid mathematics to at least support these intriguing ideas. So if these interpretations of the mathematics aren't right, there is some interpretation that would have to match. So that being said, we can now explore the strange reality of the smallest and the largest, from strings to branes. But first, we should establish a little bit of history of physics that led to these ideas. And don't worry, this is interesting stuff. It's not a boring history lesson like, you know, college professor kind of stuff. We're not doing that. So this is interesting stuff. So by now, the majority of us, we probably already know something about, or at least have heard the term, the theory of everything. It's a long sought-after theory that physicists recognize as their own holy grail. If anyone was able to discover a single unifying theory, and we'll get into what that means in a second, or a theory of everything, surely they would win the Nobel Prize, to say the least. But this begs the question, what is it and why is it important? You know, why should we care? So to answer that question, we must journey back to the time of Einstein and his general theory of relativity. Now, with this theory of gravity, Einstein was able to show that space and time were much more malleable than originally thought. With the mathematics he developed in this theory, Einstein set out to develop what's known as a unified field theory. Again, fancy term for something that doesn't need to be as complicated as it sounds. Einstein wanted to find one mathematical process that would describe all of nature's forces. So instead of having a separate set of laws for each force, he wanted to discover a way to combine them into a cohesive whole. Now, Einstein was unsuccessful in that pursuit. However, he did provide a lot of groundwork that physicists still use today in order to accomplish the same ambitions. So at the time that Einstein was on this quest for unification, which is just, again, taking all the known forces and figuring out one mathematical equation that would describe all of them. The known forces were gravity and electromagnetism at that time. So gravity was described by Einstein's own theory of relativity, while electromagnetism was described by James Clerk Maxwell through a series of equations showing the relationship between electricity and magnetism, because it used to be that electricity and magnetism were different, you know, they were believed to be totally different things. So this James Clerk Maxwell guy came along and did some fancy mathematics, and he was able to show that you could actually combine them into one thing called electromagnetism, and it's one force instead of a series of different forces. So that's what they're trying to do with the known forces today. So Einstein's goal was to develop a mathematical description that would bring gravity and electromagnetism together. So in essence, unifying them. Now, this was a monumental goal, one that Einstein was very serious about. He dedicated his life to it. He was actually so serious that he dedicated the last 30 years of his life, and actually Brian Greene explained this in his book, The Hidden Reality. So this is a quote from The Hidden Reality. Let me find it here. I had it. Okay. Brian Greene, Hidden Reality, talking about Einstein. This is a quote. His personal secretary and gatekeeper, Helen Dukas, was with Einstein at the Princeton Hospital during his penultimate day, April 17th, 1955. She recounts how Einstein, bedridden but feeling a little stronger, asked for the pages of equations on which he had been endlessly manipulating mathematical symbols in the fading hope that the unified theory would materialize. Einstein didn't rise with the morning sun. His final scribbling shed no further light on unification. Okay, so again, that's a quote from The Hidden Reality by Brian Greene, specifically pages 84 and 85. Okay, so when Einstein passed, when he died, the quest for a unification was quenched. And at the time, and up through the mid-1960s, most physicists were preoccupied with quantum mechanics and understanding the atom. So to add insult to injury, it turned out that Einstein was only working on a piece of the problem. His work did not take into account two extra forces revealed by various experiments, the strong nuclear force and the weak nuclear force. Now, the strong nuclear force, that's what holds the atomic nucleus, holds it together, while the weak nuclear force is responsible for the decay, nuclear decay, as well as other things. So it's not super important to know that, but that's he didn't know about those two forces. So unification would have to take those extra forces into account, meaning there would be the need to unify four forces, not just two. Gravity, electromagnetism, electromagnetism, gravity, strong and weak nuclear forces, so four forces. So great strides to this end were made in the late 1960s and 70s. It was already known that quantum field theory could be successfully applied to the electromagnetic force. Quantum field theory basically says that everything in existence, all fundamental particles, are just tiny vibrations in quantum fields that permeate all space. Now, it was discovered that it could also provide descriptions of the strong and weak nuclear forces. So finally, it was looking like the three non-gravitational forces could be unified, but there was a problem. When physicists tried to apply quantum field theory to gravity, the math would just fall apart. General relativity and quantum mechanics were both incredibly successful by their own right. The former for the large scale and the latter for the small scale, but they would not agree when trying to mix them together. It would seem that both would have to remain mutually exclusive, gravity and quantum mechanics. So hope was restored in the mid-1980s when a new approach of superstring theory came about. It seemed that there was finally a possibility that gravity could be included in a unified theory along with the quantum mechanics of the other three forces. So superstring theory, or string theory for short, we could call it that, took off at a fast pace. Mathematics were constructed and research was conducted and a framework was built. But there was still a lot that was unknown about string theory. In the mid-1990s, while trying to probe into the unknown, researchers found that string theory was intertwined with multiverse notions. Now, the term multiverse refers to the idea that there are multiple universes outside of our own, and the collection of our universe along with these other proposed universes, that's what's known as the multiverse. We could think of the multiverse as everything God created, even the stuff we can't see. Heaven, just everything. And that's also where the name Into the Multiverse, the show that I host for Skywatch TV. That's where that comes from. We study Into the Multiverse. Okay. So when researchers continued to try to refine the mathematics of string theory, they realized it was clearly shown that our universe could be part of a multiverse. And in fact, the math showed not only one type of multiverse possibility, but a variety in which we could be a part of. Now, when talking about the multiverse, that doesn't always mean parallel worlds that are inhabited by other versions of us and every choice creates another universe. It doesn't have to mean any of that. It could, but it doesn't have to. That's only one model, and a lot, honestly, there's a lot in that model that kind of falls apart when looked at modern physics today. That was developed, I think, in the 50s or 60s, but a lot of it doesn't hold water. When we talk about multiverse, we're basically talking about how one universe could just be one part of a extra dimensional construct. We talked in the last video about like a deck of cards. If you were to think of it in terms of a deck of cards like I have here, you can have one card, that's our universe. But if you have enough of these universes stacked up together, you have a deck. You have a three-dimensional construct. And I know technically a card is a three-dimensional construct, but just thought exercise, just for sake of argument. So you stack enough of those up. So that's the idea for our three-dimensional universe, that maybe constructs in the fourth spatial dimension or the fifth or so on and so forth. And again, we're just talking about spatial dimensions here, not time, but that our universe might be one of many that make up those other dimensions, and God very well could have done that. It doesn't mean that they have to be inhabited by other versions of us. That's not what we're talking about. But it's interesting to think about that. For more on that, check out the last video, 10 Dimensions of Heaven and Hell. So let's move on to quantum fields. Yay! By some interpretations, classical physics describes a field as sort of it is a difficult thing to explain. Sort of like a mist that fills a region of space and can contain disturbances in the form of ripples and waves. So classical physicists such as Isaac Newton taught this. And you can read more about this in The Hidden Reality by Brian Greene, or you can pick up when it's out, me and Tom Horn's new book, Abaddon Ascending. We do talk a lot about quantum field theory in there, because the more I've studied it, the more I've come to believe that this is an accurate, and actually it's the most accurate description of any scientific anything in existence. But I do believe that that quantum field theory is what reality is. But it is a bit difficult to explain what a field is, and it took me a while to kind of get it in my head too. We could think of, and I use this example in Abaddon Ascending. You could think of yourself immersed in a pool of water. All around you, there's water. Okay, so that you could think of that as a water field, in a sense. Now, of course, water is made up of molecules and atoms and all sorts of stuff. Quantum fields, they're quantum, so they're not made of anything else. But just as a thought exercise, and every point in space would have a value. So think about the air in the room that you're in right now. You could think about the air around you as an air field. So all around you, every point in space. When I say space, I don't mean outer space, just space, just space around you. Every point, there's air. And let's say that all those values, if you're looking at the temperature of the air around you, every point in space would have a different value of temperature. So the closer you are to the ground, the colder it is. Those points in space would have a colder value, whereas the higher up you go, it's hotter, so those values would be hotter. Quantum field theory is a little bit like that. If we think of like magnetism, technically electromagnetism, but if we think of like the magnetic field, around a magnet, a kitchen magnet, the values of those points in space around that magnet would be stronger because the field is being more affected there. Whereas, say, a mile away, it would be much weaker, almost non-existent. So That's basically what a field is. It's just a set of values. But ripples in those fields is what brings a particle into existence. Like the ripple itself actually is the particle. Okay, so by Maxwell's interpretation, the electromagnetic waves produced by a light source, like a light bulb, undulates across space to their destination. Maxwell showed that the waves movement he was able to show the waves movement by mathematics. So an undulating field results in undulating numbers, meaning the numerical value of the field at any given location, it fluctuates up and down repeatedly. So it's different all over. Now, when quantum mechanics is used to define a field, the result is known as quantum field theory. So quantum field theory can be set apart from the rest by two distinct features. First, the value of a field at any given point will fluctuate randomly due to something called quantum uncertainty. And you can also see also Heisenberg's uncertainty principle developed by Werner Heisenberg in 1927, which states the more precisely the position of a particle is determined, the less precisely its momentum can be known. So you can't know the position and the velocity or the speed of a particle at the same time. That's called uncertainty. So that's one aspect. Second, that a field is composed of incredibly small particles, which are known as the field's quanta, which is, a term that we already looked at. So, for example, the electromagnetic field's quanta, its particle, is the photon. So for every fundamental particle, there's a field. For every field, there's a fundamental particle. So quantum field theory, building off of and slightly modifying Maxwell's classical interpretation, shows that the light bulb emits a stream of 100 billion photons every second. So research of the past few decades shows that every field is subject to quantum fluctuations, which is just like a vibration in a field. So every field is associated with a type of particle. So electrons are quanta of the electron field, quarks are quanta of the quark field, so on and so forth. The mathematics of quantum field theory show these particles as points in space that possess no spatial extent or internal structure. It's just a fluctuation in a field. So the math is so sound, actually, that there's not only is there no experimental data that contradicts the prediction, but it actually describes the behavior of particles with incredible accuracy. So, for example, the quantum field theory of electromagnetism, which is called quantum electrodynamics, another fancy term for something that doesn't have to be fancy, it has calculations that match measurements to a precision of 10 decimal places. Which is insanely accurate. So this is a truly astounding example of how precise agreement possible between theory and experiment. So as precise as quantum field theory can be, it fails to be able to include gravity with the other three forces in a unified theory, in a theory of everything. Gravity it's different. There's something different about it altogether. When the equations of general relativity are introduced into quantum theory, the math falls apart. Now, when the mathematics are worked out, it's typical to get an answer of infinity. Now, of course, in certain areas, that wouldn't be a problem, so they say today, but some things could theoretically be infinite, and this is theoretical. This isn't the actual, what actually happens, like the size of the universe. It could be, but it's not. But when trying to figure out probabilities, infinity, it's not a valid answer. So by definition, the value of a probability has to be between 0 and 1, or between 0 and 100 when considered in terms of percentages. There's got to be a percentage. Okay, so a probability of infinity, it's completely meaningless. It shows that there's a problem somewhere in the equations. And interestingly enough, today, physicists are getting really comfortable with the idea of infinity and just saying, how sometimes as Christians, we're kind of blamed for worshiping a God of the gaps, which basically means If you don't have an answer to something, well, God did it, and then that's the answer. God just did it. Well, we're kind of criticized for that, but physicists, in my opinion, have an infinity of the gaps problem, or people who are more scientifically minded. When something doesn't make sense, it's because infinity. There are an infinite number of parallel worlds, and we're just one of an infinite number. We see descriptions like that a lot, but it's just not good enough. Just like saying God did it, while that may be true, it's not going to be a good enough answer for somebody who doesn't believe in God. That's going to be just meaningless to them. Same with the idea of infinity. That's not a good enough. It's not a good enough answer. So physicists, they were able to determine the issue was due to the fluctuations of quantum uncertainty. So by this time, mathematics were developed for the strong nuclear, weak nuclear, and electromagnetic fields. However, when the same mathematics were applied to gravity, it fell apart. So as it turned out, the fluctuations in the gravitational field, they were far more different and jarring. By comparisons, if the fluctuations of the other three forces were equivalent to a person stomping around on the floor, the fluctuations for the gravitational field would be equivalent to an earthquake. So that's due to the fact that the gravitational field is intertwined with the fabric of space and time, and its quantum fluctuations affect the entire structure. So for years, physicists largely ignored this problem because it only comes into play when considering extreme circumstances. Gravity really only makes its mark on massive things, while quantum mechanics describe things that are incredibly small. So the only time gravity and quantum mechanics come together in a noteworthy way is when something incredibly small yet incredibly dense is being considered. For example, when physicists consider black holes or the Big Bang, or things that do involve enormous mass condensed down into an incredibly small space. The math breaks down. This leaves unanswered questions from a mathematical standpoint as how the universe began and how it might possibly end. Now, of course, keep in mind, this is from the standpoint that the materialist scientific standpoint that states that God isn't involved whatsoever. Now, typically, our version of creation from Genesis and our version of eschatology from books like Daniel and Revelation would not be considered by physicists and mathematicians in working out those problems. So there's a divide there. Now, there are ways to calculate just how massive and how small a physical system, which is just a series of events, would need to be for both gravity and quantum mechanics to play a noticeable role. The result actually turns out to be the Planck mass, which we talked about in an earlier video, which, as we discussed earlier, it's 2.17645 times 10 to the negative 8 kilograms, or 10 to the 19 times the mass of a single proton. Bunch of stuff that you don't really need to know. It's squeezed down to a volume of about 10 to the negative 99. So this incredibly small volume can also be described as a sphere with a radius of the Planck length, which actually somebody left a comment on the previous video and said, wouldn't the Planck length have to be a sphere since you can't have anything thinner than it? How can the Planck length be a line? And he's absolutely right. So I forgot who exactly wrote that, but if you're watching, you were absolutely right. The Planck length already is a sphere. So due to this, quantum gravity is more than 1,000,000 billion times beyond the scales that can be probed with even the most powerful particle accelerators and technology available today. So to add even more mystery, that this unknown space between what we can observe and the Planck length could possibly be teeming with undiscovered fields and particles. There could even be other things that we have no concept of yet. So because of this, it was assumed that to unify gravity and quantum mechanics, it would mean needing the capability to explore this expanse, which for the most part is experimentally impossible at our current level of technological development. Most scientists concluded it was beyond reach, and they gave up the search for a single unifying theory. So that's why in the mid-1980s there was a great deal of skepticism when word got out that there had been some major theoretical developments towards unification by means of a new approach, string theory. That's the new approach, string theory. So the basic idea of string theory, it's not, I promise, it's not as difficult to understand as the math behind it. The actual mathematical equations behind many things discussed throughout these videos are far beyond what I personally can grasp, which is why I've chosen not to focus too much on those areas on the math. But mathematics aside, these ideas are still well within the reach of the average layperson, such as myself. So there is no need to allow the mathematical aspects to cause intimidation. Now, where did I leave off? Before string theory came along, it was widely assumed that the fundamental structure of nature was comprised of point particles with no internal structure, and that they were governed by the equations of quantum field theory. Now, you can also see what's known as the Standard Model, a theory that's commonly viewed as containing the fundamental sets of particles. But string theory redefined this assumption in some really interesting ways. Most notably, string theory suggests that particles are not merely dots. You know, they're not merely these little spheres. It's instead suggested that at their core, they are unimaginably tiny string-like filaments that vibrate. So according to string theory, it's tiny vibrating strings that make up the fundamental reality of nature. So in essence, if you looked deeply enough into any subatomic particle, you would find a string. Even more, string theory states that the strings within different particles are actually identical in nature to one another, but they vibrate at different rates and in different patterns. So the vibrations of the string is what determines what type of particle it is to be, you know. So for example, an electron, it's less massive than a quark. It doesn't have as much mass as a quark. So according to string theory, the electron's string vibrates less than the quark's string. Okay, so an analogy that's often used to describe this idea is like that of a violin. But just going to these, I'm going to switch back to screen share so I can show you an example here that might help make this make a little bit more sense. Okay, so here this is figure 28. Using the example of an oxygen atom, this shows the difference in vibration between an electron and a quark. A quark is more massive than electrons, so string theory states the quark's string would vibrate more intensely than that of an electron. Okay, so you have an electron here, there's its string, you know, kind of moving around, but here you have a quark and it's like going crazy here. So that example can kind of help. Now, that concept reflects the relationship between energy and mass that is described in Einstein's famous equation, E equals mc squared, where energy equals mass times the speed of light squared. So that actually isn't a really complicated equation. This is like the conversion rate between energy and mass. It actually shows that energy and mass is the same thing. So, an analogy for string theory, a violin. We could think of a violin. The violin is a great comparison because in reality, it contains an extraordinary amount of notes. Since a violin, it doesn't have frets like a guitar, there's a variety of different vibrations that can be achieved between musical notes in our classic scale. For example, you could play an A note and you could play a B note, but you could also play halfway in between those two notes and get an A sharp or a B flat, and that's where the division ends within our classical scale of music theory. However, within an instrument like a violin, nothing is preventing you from playing a note halfway between an A and an A sharp. So theoretically, you could keep doing this until you get down to Planck length scales, and each note or vibration would be unique. This is the idea within string theory. Every unique particle contains a string that vibrates in just the right way for that particle to exist. All strings are the same. The only difference is their vibrational patterns. So, in fact, the theory postulates that the vibrating string does not merely determine the properties of the particle that surrounds it. Rather, it is the particle. The vibrations are the particle. The string is incredibly minuscule, again, on the order of the Planck length. This essentially means strings are one-dimensional loops, in a sense. Due to the string's incredibly small size, even today's most technologically advanced equipment cannot determine the string's structure. The Large Hadron Collider bombards particles together at energies beyond 10 trillion times that of a single proton at rest and can probe scales of 10 to the minus 19 centimeters, yet that is still not enough to accurately observe the Planck length. And this is almost beyond comprehension. 10 to the minus centimeters is a millionth of a billionth the width of a single strand of human hair. Yet this is still extremely far removed from the Planck length. So because of this, strings would still appear as dot-like if observed with even the most advanced particle accelerator in the world, which it can't do anyway, but even if it could, it would still look like a dot. So despite this, string theory still states that particles are, in fact, strings. So there's much more that could be said about string theory. And because I want to get into branes, we want to talk about branes because it's interesting too. But there is a lot more that could be said about string theory. The content of which could easily fill multiple volumes of books, and has. There's a lot of different books on string theory, and we'll get more into some of that in a little bit. But what has been presented thus far is sufficient enough to understand the next topic. So we're going to talk about branes, and I think after that we're done. But if you have questions or comments, hold them to the end. I don't have the chat room up right now, but hold them to the end, and I'll answer your questions if you have them. Because again, now that's if you're watching live. If you're watching this, you know, as a pre-recorded deal. If you're watching this after the live thing, obviously I can't do that. But if you have a question, you can email me at jpeck@skywatchtv.com, and I'll be happy to answer your questions. Okay, so branes. When string theory first came about, and for some time afterward, the idea of branes was largely ignored. As it turns out, however, branes and strings actually go hand in hand. String theory is no longer a theory of one-dimensional strings, but it's also a theory of branes that can extend in 2, 3, and even higher dimensions. So branes, it's B-R-A-N-E-S. It's short for membranes. They were first introduced into the world of physics in 1995 when physicist Joel Palczynski of the Calvi Institute for Theoretical Physics, or KITP, in Santa Barbara, established that they were essential to string theory. So before this, there were propositions of brane-like objects by certain physicists. One example is what's known as a P brane, and it's the letter P dash brane, and I'm sure the pun was intended in naming that one. Which is an object that can extend infinitely far, but only in some dimensions. Physicists were able to determine this by means of Einstein's theory of general relativity. There were also suggestions describing ways of confining particles to brane-like surfaces. However, the branes that Palczynski proposed were the first known type that could confine both forces and particles. So as it turns out, lower dimensional branes can theoretically trap particles and forces, even if the universe has many other dimensions. So if string theory is accurate, then there's no getting around acknowledging the possible existence of branes. Now, earlier in another video, we discussed how looking at lower dimensions can help put higher dimensions into perspective. We use the analogy of flatland, and we also realized how the two-dimensional flatland would be just a slice of a three-dimensional world. Again, like a card in a deck of cards. You can go to the 10 Dimensions of Heaven and Hell video for more on that. And we also suggested that our three spatial dimensions would be just a slice of a higher dimensional reality. So branes can be understood in that same way. So in essence, a brane, it's a region of space-time. They say space-time because time is woven into space. So it's a region of space-time that permeates through a slice of space, which in itself could be multi-dimensional, which would be called hyperspace if you're talking about space in higher dimensions. So the reason that they are equated to membranes is because membranes are layers that either surround or extend through a substance. Branes can either be slices inside space or slices that surround space, much like a sandwich with the bread representing the brain and the lunch meat representing space. Okay, so now that physicists have had time to go over the theories of mathematics, they have come to the conclusion that 3 dimensions of space in which we exist could be a 3-dimensional slice of a higher dimensional reality. They have been able to define several characteristics of branes. For example, a brane would have to have fewer or occasionally the same number of dimensions than the higher dimensional space surrounding or bordering it. As long as that's maintained, branes can have any number of dimensions. So branes can exist as boundaries between higher dimensional space, and that higher dimensional space, sometimes it's called hyperspace. A lot of times physicists will just call it the bulk. You can kind of think of it like a box. And the walls of the box are the branes, and the space inside the box is the bulk. So when considering a higher dimensional reality, branes would be the boundaries of the full higher dimensional space known as the bulk. The bulk and branes are completely different things. The bulk extends in all directions and spans all dimensions. And because of this, the bulk is recognized as bulky, while branes are flat by comparison and only in some dimensions. If a brane borders the bulk, some of the bulk's dimensions would be parallel to the brane, while others would lead off of it. So when something such as a particle reaches a boundary brane, it bounces back. Think of a ball inside of a box, and you throw it in there, it's gonna, it can bounce around in there. So that's known. It has just, these terms are just ridiculous. Reflective boundary condition. That's what's known as and I'm sorry for the terms. I mean, they should be simpler. But the interesting thing about this is energy is not lost, nor does the particle get absorbed into the brane. The brane is the end and nothing gets beyond it. So the boundary brane is the end of dimensional existence. Branes also have the characteristic of trapping things on lower dimensional surfaces. It conveys the idea that in a reality with extra dimensions, not all matter is able to travel everywhere. Particles or strings can actually be confined to a 3-dimensional brane within a higher dimensional reality. So you think about like a playing card and you put a sticker on it or something. It's bound to that, if we think of this as a brane, it would be bound to that. So brane-bound objects, they lack the ability to travel through extra dimensions that extend off of the brane due to physical laws. So not every particle would have to be bound to the brane. Some might be free to venture out into higher dimensions. But regardless if the brane in question is slack or if it can move or if it's taut and sits still, the particles that are bound, they never leave. They can't become unstuck. So as we stated before, branes and the bulk could have any number of dimensions as long as the brane has less dimensions than the bulk. So the number of dimensions that brane is confined, that a brane-confined particle can move around is what's known as the dimensionality of a brane. Again, one of those terms. The easiest to consider is that of three spatial dimensions, because that's what is most relatable to us as three-dimensional beings. The universe could have many dimensions. But if particles and forces are trapped on a brane that extends in 3 dimensions, they would still behave as if they only occupied 3 dimensions of space. So particles and forces that are trapped on a brane can only move along that brane's dimensions. So the interesting thing is, as mentioned before, there are things that physicists can never that physicists know cannot be trapped on a brane, and gravity is one of those things. So according to Einstein's general relativity, gravity is woven into the framework of space and time. This means that gravity must be able to extend through every dimension of space and time. General relativity would have no meaning if gravity could be confined to a brane. So gravity is not confined on these branes. So the idea could very well lead to an answer of the gravity problem in unification. It could help explain why gravity is so weak and vastly different compared to other forces. If the other forces, along with the rest of the universe, are bound to a brane, yet gravity is free to roam the bulk, we should expect gravity to be weaker and different. And that's an idea that physicist Lisa Randall proposes in great detail in her book, Warped Passages, so you can check that out. But anyway, so now that we have a basic understanding of branes, it's just the boundary, you know, we can integrate strings and discover how they tie in. No pun intended. As stated earlier, with modern string theory, branes must be considered. Gone are the days when you could have one without the other. All right, so I'm going to put screen share on again because there's something that we're going to look at. Start screen share. There we go. Okay, in 1989, a type of brane known as the D brane was first discovered in the equations of string theory by Jin Dai, Rob Lee, and Joe Polchinski. String theory shows that strings can either be closed loops or open-ended. For string theory to work, the string's open ends would have to go somewhere. And the only location that string theory allows for the open ends of strings to be is on the D brane, figure 30. So that's what we're looking at here. The D in D brane is actually named for Peter Dirichlet, a German mathematician who lived in the 19th century. Okay, so this figure, this shows how open strings, such as with electromagnetic particles, remain attached to a brane, while open strings are free. This shows how open. Wow, I messed that up. This is supposed to be closed strings. I've had this book out for like 2 years and I didn't realize that. Okay, closed strings are free to travel the bulk. Okay, so like here, these loops, they're not connected to the brane, so they can float freely in the bulk. Now these electromagnetic particles, they live on the brane. They are connected. Their ends of the string are connected to the brane, so they are not free. Okay, so since the bulk can contain more than one brane, not all open strings have to end on the same brane. So we're going to look at that over here. Okay. String theory tells us how many dimensions these branes would have. As stated before, branes can conceivably extend into any number of dimensions. Typically in string theory, the way branes are labeled is to use the number of spatial dimensions, not temporal. We're not talking about time, just dimensions of space, in which they extend. For example, a brane that extends in 3 dimensions would be called a 3 brane. Okay, here, figure 31. This is an example of a string that has 2 ends attached to different branes. So you can have particles where the 2 ends are on the same brane, or they can attach into different branes. So this idea of open and closed strings is what makes branes so important to string theory. Gravity is thought of being in the form of a closed string that makes up the graviton particle. Since the string is closed and it's not connected to the brane, this would allow gravity freedom to travel through the bulk, while the rest of the forces, being open strings and connected to the brane, would not possess that freedom. So that's what we have here in figure 32. This shows how gravity can escape into the bulk while ordinary matter cannot. This is what defines the difference between closed strings and open strings. So you have this square here is a brane. These black dots, that's matter on the brane. But here's gravity. Gravitons can escape the brane and go on into the bulk. So this could be the answer to why gravity is so much weaker than the other three forces. There is also the possibility that this could lead to a single unifying theory of all four forces, which would absolutely drastically change our world. If a single unifying theory was ever discovered, it would be a game changer. So you simply cannot have strings without branes. Okay, before 1995, 5 versions of string theory existed. Each version included different forces and interactions. Then, in 1995, at a conference at the University of Southern California, theoretical physicist Edward Witten shocked the string theory community by showing various dualities in the five versions. So in particle physics and string theory, a duality describes when two theories are actually the same theory with different descriptions. Okay, so I guess I can take it back off screen share here because those are the end of the figures for that. Hello again. Okay. So in essence, Witten showed that each of the 5 versions were looking at different aspects of the same issue. So with the added understanding of branes, the 5 apparently different theories were shown to be the same theory from different vantage points, all of which were valid and true. Witten gave this new theory the name M theory. So when we talk about M theory, that's what we're talking about. And interestingly enough, to this day, Witten has not revealed what the meaning of the M in M theory stands for. Some theorize it might stand for magic or mystic, or might even represent the first letter of Witten's last name only upside down, an upside down W. Who knows? He hasn't told anybody. If I ever get the opportunity to interview him, I will ask, and he probably won't tell me. But anyway, so there's still a lot unknown in M theory even today. No one knows the best way to express and formulate M theory, but most string theorists recognize this as their primary goal. M theory offers a lot of potential within the physics world. It could give a more unified picture of string theory's potential as a theory of quantum gravity. Now, while many of these things within this video and throughout all these videos, they may seem strange and impossible or maybe even confusing on the surface, we have to remember that God, the ultimate creator, he's not bound by our perceptions. Imagine how strange it would have sounded the first time people heard Galileo postulate that the Earth, in fact, revolves around the sun and not the other way around. Now, we might think of that as slightly humorous today, but if these theories of strings and branes prove to be true in the future, we could easily find ourselves falling into the same trap as Galileo's detractors if we're not careful. Now, I do agree it is always good to maintain a healthy amount of skepticism, but I think Proverbs 18:13 states it best when it says, "He that answereth the matter before he heareth it, it is folly and shame unto him." So we should at least consider these things, hear these things out, consider the possibilities before making a final assumption. Okay, the continuous, we're going to end with this, and then I'll get into the chat room. Stay on this video once I'm done, because I'm going to get into the chat room, and I'll talk with you, answer some of your questions. The continuous spoken word of creation, that's one last thing that I want to consider concerning string theory and quantum field theory, all these strange things, particles. There is an interpretation of Hebrews 11:3 that states God not only spoke everything into existence, but that he is still in the process of that spoken and creative word. Because remember, this idea, since God is outside of time, his spoken word is eternal and is holding reality together from the beginning of time as we know it till the end of time as we know it. So Hebrews 11:3, it states, "Through faith we understand that the worlds were framed by the word of God, so that things which are seen were not made of things which do appear." So this is a particularly interesting concept concerning string theory. If string theory or quantum field theory ever proves to be true, it could be that the vibrations in the strings are actually caused by higher dimensional sound waves, just for lack of a better term, from the eternal voice of the living God, of God. Of course, I say sound waves for lack of a better term, and this idea is speculative, but it's definitely interesting to consider. If God is outside of time, his voice, his creative voice, would not be subject to time, but could exist within it, outside of it, all around it, and everything between. So it's definitely interesting to think about. I am going to get into that is the end of this, but stay in the chat room, because I'm going to read some of your questions aloud. I'm going to keep this video going for a little while. I'm interested to know what you think. Give me 1 second while I get into the room here, and I got to make sure to mute myself so I don't accidentally. Okay. All right. It is good to see you. We got 25 people watching now. Linda says, thank you, Josh, for leaving the math out and presenting the topics of string theory. You're very welcome. 1/1,000,000th of a billionth, my brain hurts, says Rick. Mine does too. I totally understand. Can string theory and quantum entanglement coexist simultaneously? Actually, yeah. Both could be true. Now, I don't know, Linda wrote that. I don't know if you mean quantum entanglement or quantum field theory. Quantum entanglement is the ability for photons to speak or communicate with one another at instantaneous speeds. Quantum field theory sometimes is seen as competitive with string theory, but really both of them could exist. What would have to happen, though, is there would have to be a fundamental field that all other fields come out of. There would, in a sense, there would have to be like a string field for that to work. So that's, but yes, they could coexist. Hey, James DeWitt is on. Hey, James, how you doing? And they say science proves the Bible, but nowadays I say more so that true science is proven by the Bible. Yes, and I agree. I absolutely agree. Does anybody else have any more questions? I'll kind of cycle through the chat room here and see, but go ahead and leave some questions. Let's see. Vibration seems to be a keyword in this subject. 10 dimensions of heaven and hell, reality boundaries, parallel worlds, extra dimensions video at YouTube by Josh was really awesome. Thank you, Rick. I appreciate that. That means a lot. Josh Peck, one of the best sources on metaphysics, in my opinion. Thank you. Looking for some questions here. Calling support group, download the Pray With Me app. Well, thank you for advertising on my video. Brandon says, live, huh? Josh, good Sunday to you. LOL, 2 voices, parallel universe. LOL, thank you. Good Sunday to you, too. Great explanation. My 10-year-old is listening with me and learning. Great. I know some of the stuff in that, some of the stuff in this video is a little confusing, but a lot of it I found really comes through repetition. The first time I heard this stuff, I mean, I didn't understand any of it. But it comes through repetition. And I think that having the book, this all comes from my book, Quantum Creation. Having the book in print can help out a lot too. Okay, so I'm not seeing anybody else really saying anything or asking anything, and that's okay. If there are no other questions, I will end the video, but I do want to thank you all. Thank you all for joining me in this. I know this one was a little heavier than usual, but the next video I do, we're going to take a break from a lot of this particle physics stuff, and we're going to get into time. And actually, I'm going to, I did an interview with Dr. Ronald Mallet, and if you've never heard of him, check him out. He's an expert in time and black holes and things. He gave me an interview for my book, Quantum Creation. And it's a fantastic interview, and it was a lot of fun. But I want to share that interview with you in the next video. And it's all about the hypotheticals of time travel and is it possible? How could it be possible? It's just a fun conversation. So we're going to get away from a lot of the more sciencey things and talk more hypothetically. So it'll be fun. Watchman Living Stone says, what do you know about dodecahedrons, Josh Peck? And he also says, Revising Reality was awesome, by the way. Thank you very much. I appreciate that. Revising Reality, for those who don't know, it's a book that I, with Doug Woodward and Gon Shimura and Anthony Patch, we pooled our resources together, put out a book called Revising Reality. You can go to sharpeningreport.com and get it there. We had a lot of fun doing it, and I really believe in the project. It's a good book, so I'm glad that you enjoyed it. Dodecahedrons. I don't know as much as Anthony Patch does. That's more his area of expertise, and I wouldn't really have anything to add. But I will say that the 100th episode of the Sharpening Report, I did an interview with Doug Woodward and Anthony Patch on that topic that you can check out. It's TSR 100. It has Anthony Patch in it. It turned out really good. So that might help explain more. But yeah, again, that's more Anthony. And we are in a future episode. We are gonna, or maybe multiple episodes. I'm not sure how we're going to divide it out, but we are going to have Anthony Patch, Doug Woodward, and Gon Shimura on the Sharpening Report, and we're going to all talk about Revising Reality. I'm going to come on the Sharpening Report as a guest, and either James DeWitt or Jake Rahutsky, or a combination of the two. I don't know exactly. We're still figuring it all out, but one of them will host it, and it'll be a lot of fun. But thank you for the question. Basically, my opinion is probably whatever Anthony Patch says about it is the way to go, because I don't know any alternatives. But yeah, so that's that. Linda says, thank you, Josh. Looking forward to your next video. I'm looking forward to it too. I think it's going to be, I think it's going to be more fun. Not that this one wasn't fun, but with this one, we got into a lot of the more science-y stuff, and I could see how that could be sort of dry to some people, but it's still important, for the foundations of things that we're going to be talking about. So yeah, next video, and really I think every video after that until we get through the whole quantum creation book, I think that it'll be a little easier going. Watchman Living Stone is asking if I've ever talked to MickWick77. Can't say that I have. I have not heard of that person. James DeWitt writes fantastic stuff, presenting in a palatable form to the rest of us, which is a real gifting. Thanks, Josh. You are very welcome, James. It is my absolute pleasure, and I love doing this stuff, and I never want to lose the ability to explain it to a general audience. I do still consider myself very much a layman. I didn't go to school for this stuff. I just love it, and I research it in my own time, but I do want to make sure that I don't overcomplicate things ever, and all that stuff. So, but I'm glad that I've done that. Give me 1 second. Okay. Watchman says, your info is always welcome and enlightening. Peace, love, grace be with you. Same to you, Watchman, and same to everybody, everybody who has been watching and who continues to watch. Again, if you haven't done so, subscribe to my channel. And this isn't only my channel. It's also James DeWitt's and Jake Rahutsky's, for as long as they want it to be. But James is going to be posting more stuff. He actually did a couple of really cool interviews that we're going to be releasing soon. So stay tuned for just some cool stuff coming out. Okay, I'm kind of rambling now, so I'm gonna end this video. But thank you again all for watching. Next time I do one of these, we'll talk about time travel. It'll be a lot of fun. So everybody have a great Sunday, and as always, take care and God bless.